Hello everyone, I'm Tongtong from University of Birmingham. Today the topic of my presentation is about the cryogenic thermoelectric generation with cold recovery from liquid air energy storage. My presentation will be divided into these 5 parts. So first I will give you a quick through of the background of my research. As we all know that the cryogenic exergy of the liquid air consists of 2 parts. The first is the thermal component and the other is the mechanical component, or we can also call it pressure component. And in the standalone liquid air energy storage system, the mechanical component is utilized to generate electricity directly. And the thermal component is recycled, stored, and reused in the charging process to improve the liquid yield. And it is one of the best ways to improve the round-trip efficiency of the standalone liquid air energy storage system. But in some other application scenarios, it may not. So first scenario is when the cold energy is surplus in the system and more cold energy cannot contribute to the improvement of the liquid yield. For example, in this RAS RNG system, the cold energy of RNG is used in the charging process to produce liquid air. So during the discharging process, the cryogenic energy of the liquid air is wasted directly. And the other application scenario is when the charging process and discharging process cannot operate in the same place. For example, the charging process of the liquid air energy storage system could build nearby a renewable energy power plant to produce liquid air. And then the liquid air tank could be loaded in an electricity bus for both electricity and cooling supply for users. And in the electricity bus, 15-degree cold is cold enough for cooling use. So most of the cryogenic energy of the liquid air is wasted as well in this application scenario. So to deal with this problem, there are some traditional ways. For example, we can use Rankine cycle or Brayton cycle to recover this part of cryogenic energy of liquid air for power generation. But there are also some disadvantages which limits its development in some small-scale application. For example, high-level equipment requirement, high capital cost, low rate of return on investment, and so on. So in our research, we propose to use thermoelectric generator to recover this part of cryogenic energy of liquid air. For power generation, thermoelectric generator is the most effective way to generate electric current from a temperature gradient directly. And this figure is one of the TEG module, which is the basic element in the thermoelectric generator. And in the previous study, most of the researchers, they focus on the waste heat recovery by the thermoelectric generator, and the thermal efficiency could only reach 5%. And a company named Solid Seal, they proposed to use a thermoelectric generator to recover the cryogenic energy. So the thermal efficiency could be increased to 10% based on the experiment data. So based on the setup of their experiment, we built the thermodynamic model for a cryogenic TEG heat exchanger. The left figure is the overall structure of this cryogenic TEG heat exchanger, and the right figure is the simplified layout of the thermoelectric modules in this heat exchanger. As we can see that there are M modules in one column and N thermoelectric modules in one row. And the temperature distribution of every single thermoelectric modules in one column are almost the same. So we only pick up one row of the thermoelectric modules to build the thermodynamic model. And we choose the liquid nitrogen and hot oil as the cold source and hot source respectively for the research. And first we started the effect of the load on the working performance of the cryogenic TEG. And from these two figures, we can see that no matter how we change the mass flow rate of the cold source and hot source, the maximum power generation always occurs when the load is equal to the internal load of the cryogenic TEG heat exchanger. And the maximum thermal efficiency always occurs when the load is 1.2 times of the internal load. And then we also studied the effect of the mass flow rate of the hot source on the working performance of the cryogenic TEG heat exchanger. As we can see from these two figures, that increasing the mass flow rate of the hot source could contribute to the improvement of both the power generation and thermal efficiency of the cryogenic TEG. But considering the design of the heat exchanger, the mass flow rate difference between the hot source and cold source can differ a lot, so we choose 5 for the following study. And then we also studied the effect of the temperature of the hot source on the performance of the cryogenic TEG. And from these two figures, we can see that the higher the temperature of the hot source, the higher the power generation and thermal efficiency we can get from the cryogenic TEG heat exchanger. And that means that if we can introduce some waste heat into this system, we can improve the working performance of the cryogenic TEG heat exchanger further. And finally, we studied the effect of the number of the thermoelectric modules on the working performance of the cryogenic TEG. We increase the number of the modules from 50 to 100. And from these two figures, we can see that when 100 modules are used, we can have a higher power generation but a lower thermal efficiency than the 50 modules. And to explore why we get these results, we analyze the temperature profile and the power generation profile of the cryogenic TEG heat exchanger. And the left two figures is when we use 50 modules. And we can see that only the latent heat part of the nitrogen is utilized for power generation when 50 modules are used. That makes the temperature difference of the cold junction and hot junction of every single thermoelectric modules could be about 240 degrees C, and making the power generation of every single thermoelectric modules could in the range of 1.8 to 2 kg per kilogram. But when 100 modules are used in the heat exchanger, not only the latent heat, but part of the sensible heat of the nitrogen are utilized for power generation. And that makes the temperature difference between the hot junction and cold junction of every single modules decrease from 240 to 140 degrees C, and making the power generation of every single module decrease from 1.8 to 0.6. And that's the reason why 100 modules could have a higher power generation but lower thermal efficiency than 50 modules. And in the left figure, we can see that the blue curve is the efficiency and the black curve is the power generation. We can see that when 50 modules are used, we can get the highest thermal efficiency of the cryogenic TEG heat exchanger. And that means the latent heat part of nitrogen is utilized fully at this point. And with more modules are loaded in the heat exchanger, the sensible heat part of nitrogen starts to be utilized. So the thermal efficiency starts to decrease, but the power generation could still keep increasing. But when 125 modules are used in the heat exchanger, we can get the highest power generation. After that, more thermoelectric modules will no longer contribute to the improvement of the power generation. So to compare the working performance between the cryogenic Rankine cycle and the cryogenic TEG heat exchanger, we also built the thermodynamic model of the cryogenic Rankine cycle, both the single stage and the two-stage tap. So the results are shown in the form. As we can see, for one-stage Rankine cycle, when argon is used as a working medium, we can get the highest thermal efficiency. And when methane is used as a working medium, we can get the highest power generation. For two-stage Rankine cycle, we can see that when argon and ethane are used as a working medium, we can get both the highest power generation and the highest efficiency. So if we only consider the efficiency and the power generation, from the results, we could see that Rankine cycle could perform better than the cryogenic TEG heat exchanger. But in most of the scenarios, we can not only consider thermal efficiency, we need also consider the economic performance. So we introduce levelized cost of energy to evaluate the economic performance. So we calculate the levelized cost of energy for both cryogenic TEG and cryogenic Rankine cycle, and the results are shown in this form. And we can see from this form is the cryogenic TEG heat exchanger could have a much lower capital cost and levelized cost of energy than the Rankine cycle, which means the cryogenic TEG heat exchanger could have a higher rate of return on investment and shorter payback period, and making it more attractive in some small-scale application scenarios. So finally, I will give you some conclusion and remarks of this research. First, increasing the temperature and flow rate of the hot cells could enhance the output power and the efficiency of the cryogenic TEG heat exchanger. Thus, if possible, waste heat should be introduced into this system to improve the working performance. So second, when the latent heat part of the nitrogen is fully utilized, the thermal efficiency of the cryogenic TEG could reach maximum. When some sensible heat of nitrogen is utilized, the cryogenic TEG heat exchanger could achieve more power generation, but a maximum value still exists. Third, in terms of the thermal efficiency and the power generation capacity, cryogenic Rankine cycle performs better than cryogenic TEG. However, cryogenic TEG has much lower levelized cost of energy than cryogenic Rankine cycle, which makes the cryogenic TEG heat exchanger more suitable for integration with liquid air energy storage system in some small-scale application scenarios. That's all. Thank you very much.